In the previous video, we've talked about atoms consisting of a central nucleus that is surrounded by one or more electrons, wherein the nucleus is positively charged, composed of both protons and neutrons. We've also learned from the previous video that the number of electrons is equal to the number of protons, and that the number of neutrons is obtained from the difference of the atomic mass and atomic number of a chemical element. Now, in this video, we will continue our discussion on the Bohr's model of hydrogen atom and how we've come up with energy quantization. Now let's start with electric potential energy. By definition, electric potential energy is a potential energy that is measured in joules that results from conservative Coulomb forces and is associated with the configuration of a particular set of point charges within a defined system. So, the change in electrostatic potential energy of a point charge that has moved from the reference position to position R in the presence of an electric field is the work done by the electrostatic force to bring it from the reference position to that position R. Consequently, the electric potential energy is equal to negative K E squared over R, where K is the Coulomb constant and R is the radius or the distance between the electron and the proton. The negative sign arises from the charge negative E on the electron. Combining the electron's kinetic energy and the system's potential energy, the total energy of the atom is 1/2 mv squared minus ke squared over r. The electron is modeled as a particle in uniform circular motion. So the electric force K E squared over R squared exerted on the electron must equal the product of its mass and its centripetal acceleration, that is V squared over R. So V squared is equal to K E squared over M times R. Plugging in your V squared, the electron's kinetic energy is now 1/2 K E squared over R. And for the total energy of the atom, we now have 1/2 K E squared over R minus K E squared over R, now equal to negative 1/2 K E squared over R. Now, Bohr suggested that the size of an allowed electron orbit is determined by a condition imposed on the electron's orbital angular momentum, and that the allowed orbits are those for which the electron's orbital angular momentum about the nucleus is quantized and equal to an integral multiple of h bar that is equal to h over 2 pi. So the angular momentum mvr is equal to n h bar, where r is the orbital radius. Getting an expression for the electron speed v, squaring it, and equating it to the previously obtained v squared, the radii of the allowed orbits is now equal to n squared h bar squared over mass of the electron times Coulomb constant K times E squared, where n is a positive integer. Now this shows here that the radii of the allowed orbits have discrete values, meaning they are quantized. The result is based on the assumption that the electron can exist only in certain allowed orbits determined by the integer n. So the orbit with the smallest radius, called the Bohr radius A0, corresponds to n equal to 1 and has the value 0.0529 nanometer. Hence, the general expression for the radius of any orbit in the hydrogen atom is n squared times a naught over z, where z is equal to 1 for hydrogen atom, and that the quantization of orbit radii leads to energy quantization. An, or E sub n, is equal to negative k E squared over 2 a naught times z squared over n squared. So E sub n is equal to negative 13.606 electron volts over n squared. The lowest allowed energy level, the ground state, has n equal to 1 and energy E equal to negative 13.606 electron volts. The next energy level, which is the first excited state, has n equal to 2 and energy E equal to E sub 1 over 2 squared equal to negative 3.401 electron volts. From the energy quantization, the frequency of the emitted radiation is found from the energy conservation expression E sub I minus E sub F equal to HF, where E sub I is the energy of the initial state, E sub F is the energy of the final state, and that E sub I should be greater than E sub F. So E sub I minus E sub F is equal to negative k E squared over 2 a naught times 1 over n sub I squared minus 1 over n sub F squared. Rearranging this expression, the frequency of the photon emitted when the electron makes a transition from an outer orbit to an inner orbit is E sub I minus E sub F over H equal to k E squared over 2 a naught H times 1 over nf squared minus 1 over ni squared. Because the quantity measured experimentally is wavelength, it is convenient to use C equal to lambda f to express this equation in terms of wavelength. So we replace the left side term into 1 over lambda, or frequency f over speed of light c. To balance the equation, we've also added c in the denominator of the right side term. Remarkably, this expression, which is purely theoretical, is identical to the general form of the empirical relationships discovered by Balmer and Rydberg, wherein this term here is equal to the experimentally determined Rydberg constant. So in this figure is an energy level diagram for the hydrogen atom. Quantum numbers n are given on your left, and energies in electron volts are given on your right. The colored arrows for the Balmer series indicate that this series results in the emission of visible light, while the rest of the series results in the emission of ultraviolet and infrared radiation. So that ends the part 2 of our lecture video, and thank you for watching.